Hey everyone, welcome back to the channel. I hope you are doing great. In today's video, we are going to solve one of the most classic and frequently asked interview questions, two-sum. Let's go through the problem statement. Given an array of integers nums and integer target, return the indices of the two numbers such that they add up to the target. Three important points to note. First, each input would have exactly one solution. Second, you may not use the same element twice. Third, you can return the answer in any order. Let's walk through an example to make this clearer. Here is a real world example. Let's say you have a travel budget of $500 to book two flights, one for yourself and one for your friend. You check a website and here are the flight prices. This is a method signature where travel budget is target and flight prices are integer array. Now, the task is to find two flights whose total cost is exactly $500. Just by looking at the flight prices, we can say 200 plus 300 is equal to 500. So 200, 300 is our two-sum pair. As per the problem statement, we should return the indices of these two numbers. Let's draw indices. The index of 200 is 1 and the index of 300 is 3. So the output would be 1, 3 or 3, 1 because we can return the answer in any order. We now understand the problem fully. Let's solve it using brute force first. Okay, so how would a human naturally solve this? We would pick one item, then look at every other item to see if it matches. The idea is simple. Take the first number in our nums array, then iterate through all the remaining numbers in the array. For each pair, check if their sum equals the target. If it does, we found our indices. Let's visualize this with our example. Here is the input, two parameters, an integer array called nums and integer target. To check all possible pairs, we will use two nested loops. The outer loop starts with I set to 0 and inner loop starts with j set to I plus 1. So first pair is 150, 200. Is 150 plus 200 equal to 500? No. Let's increment j and check with the next pair. Is 150 plus 400 equal to 500? No. Increment j. Is 150 plus 300 equal to 500? No. Increment j. Is 150 plus 250 is equal to 500? No. Now the inner loop ends and the outer loop increments by 1. Then the inner loop starts again from I plus 1. Is 200 plus 400 equal to 500? No. Increment j. Is 200 plus 300 equal to 500? Yes, we found it. Return indices 1 and 3. If 200 plus 300 was not 500, we would continue checking remaining pairs until we found the answer. Let's see the implementation. We have two nested loops. The outer loop starts with I is equal to 0 and the inner loop starts with I plus 1. If the sum of the pair equals the target, return the indices. If no solution found, then return an empty array. But in LeetCode, it's guaranteed to have 1. As you can see, this involves checking every possible pair. This works, but this is not the most efficient way. For small arrays, this is fine, but imagine an array with a million numbers. That's a trillion operations. That's not ideal for larger data sets. This is why we often look for more optimized solutions. The key insight for a faster solution is this. Instead of searching for the second number for each nums of I, what if we could instantly know if the complement exists and where it is? The complement is the number we need to reach our target. If nums of I is our current number, then complement is equal to target minus nums of I. For instance, if I is pointing to 300, then the complement is equal to 500 minus 300, which is 200. To check if the complement exists and where it is, we would use HashMap data structure. Using HashMap is like having a lightning fast lookup system to store and instantly check if something exists and its associated information. In our case, it's position or index. Here is how the HashMap approach works. We will iterate through our nums array just once. For each number nums of I, calculate its complement, target minus nums of I. Then we ask our superpowered HashMap, hey, have you already seen this complement anywhere? If the HashMap says no, that's okay. We just add the current num and its index to our HashMap. We store it just in case it becomes the complement for a later number we encounter. If the HashMap says yes, congratulations, we have found our pair. The HashMap will tell us the index of that complement because we stored it when we first saw it. We then return that index and the current nums index. Mission accomplished. Let us illustrate with our flight example. Initially, HashMap is empty and the I is equal to 0. So nums of 0 is 150. Step 1, calculate complement. Complement is equal to 500 minus 150 is equal to 350. Is 350 in HashMap? No. Add the current number, which is 150, and its index 0 to the HashMap. Increment I. Nums of 1 is 200. Complement is equal to 500 minus 200 is equal to 300. Is 300 in HashMap? No. Add the current number, which is 200, and its index 1 to the HashMap. Increment I. Nums of 2 is 400. Complement is equal to 500 minus 400 equal to 100. Is 100 in HashMap? No. Add the current number, which is 400, and its index 2 to the HashMap. Increment I. Nums of 3 is 300. Complement is equal to 500 minus 300 is equal to 200. Is 200 in HashMap? Yes. Its index is 1. We found our pair, return 1, 3 and we are done. This approach ensures we only iterate through the array once and each lookup in a HashMap is extremely fast. Let us look at the code using Java as an example, but the logic applies to most languages. Here is a method signature, 2 input parameters, integer array and integer target. Return type is integer array. Create an empty HashMap to check if the complement exists and where it is. Iterate through the array with index. Calculate the complement needed. Check if the complement is already in our map. If yes, we found our pair. Return the index of the complement from the map and the current index I. If not, add the current number and its index to the map. This prepares it for future checks. If no solution is found, return empty array, though the problem states there will be one. This solution is fast, clean and uses a common interview technique, hashing. Let's copy and paste the solution into LeetCode. Submit. Awesome. Solution accepted and all test cases passed. Let us analyze the time and space complexity of both the approaches, the brute force method and the optimal HashMap solution. In the brute force approach, we use 2 nested loops to check every possible pair of elements in the array. So the time complexity is of n square, quadratic time. And we don't use any additional data structures here, just a couple of variables to store indices. So the space complexity is of 1, constant space. In the optimal solution, we go through the array just once and each map operation is lightning fast with O of 1 time complexity. So overall time complexity is of n linear time. The trade-off is that we are using extra memory to store our hash map. In the worst case, we might store almost all the numbers from the list. So our space complexity is also of n. It is a small price to pay for such a huge gain in speed. So the two-sum problem is a fantastic way to understand the power of choosing the right data structure. While brute force is straightforward, the HashMap approach is a game changer for efficiency. Mastering this difference is key to becoming a more effective programmer. If you found this helpful, drop a like, subscribe to the channel and comment which problem you would like me to cover next. Thanks for watching and keep coding smart.